Can you start the recording? Okay, it's a great pleasure to have David Berenstein today from Santa Barbara. Most of you will know him maybe from his work on ADCFT, but today he'll talk about some more recent research, which goes back to quantum mechanics and applications of the bootstrap. So we're very happy to have you here, and please go ahead.
Okay. The work I'm going to talk about is some recent work on the bootstrap. This was done with one of my graduate students, George Halsey, who did a lot of the numerics and the plots. And then this is based roughly on these ideas by Han Hartnoll and Kruithof. They wrote this paper about bootstrapping methods in quantum mechanics and matrix models. And the point is that, it seemed to work well, but, we didn't have any measure of convergence. So we wanted to understand how well does it actually work in practice. And then I'll explain what the method is in general. And then there's some papers that came out roughly at the same time by a group in India, by Bhattacharya and company, and the Japanese group, Aikawa, Morita, Yoshimura. There's some more recent work too. And then there's also this paper of Chermakov and Florence from Grenoble that I'll tell you about a little bit later on. Okay. So what's the idea? So this is a statement that usually works better in mathematics than in physics, but it still works in physics, is that it's always nice to have more methods to solve all problems. Physicists tend to discard this, but in mathematics, this is a lot more important because usually the new methodology can sometimes solve problems that weren't solvable before. And then this is a reminder that if you actually look at your favorite quantum mechanics problems, even in one dimension, most of them are not soluble analytically. And in just for one-dimensional problems, the usual second-order differential equations can be solved numerically rather well. So this is not a statement where it's not that you cannot solve them at all. You can solve them numerically rather very efficiently. And then it's always nice to find ones that are analytically soluble, but it's not required. And computers are fast enough that this is not really an issue. So the bootstrap that I'm going to tell you about is a numerical method that can be used to solve these same problems. Hopefully, it'll eventually give us some hint as to better ways of solving them. Because it converges very quickly, it can be used to do precision quantum mechanics as opposed to just, getting the first 3 digits of something to the 1 per thousand. This one, you can get a lot of digits at very little cost in some sense. So this talk is really about how the method works in practice, not at the level of theorems. So I'm going to tell you what the ingredients are. The bootstrap method that I'm going to talk about uses a positivity constraint on an infinite dimensional matrix. I'll explain how that matrix is obtained. And then it depends on some parameters. And then at least the way we implemented it, you kind of do brute force search on the parameter space and then find the spots that pass the constraints. And since you cannot check an infinite dimensional matrix directly on a computer, you basically truncate it to some size and then you make it bigger and bigger. And then the constraints improve as you make the matrix bigger. The matrix components are obtained by linear recursion from some initial data. And that initial data defines, in some sense, the parameter space. And then one can obtain both the ground state and excited levels with many Hamiltonians. And the convergence seems to be exponentially fast when it works. Okay? And there are cases where it doesn't quite work. And then we're still trying to figure out why. Okay? So that's where it really becomes math. At this stage, I'm just going to tell you about the numerical method and what the ingredients are, and relations to some problems in math that it's related to. Okay, so the structure of the talk is I'll first talk about some basic stuff of observations on normalizable energy eigenstates of a typical quantum mechanical problem. Then I'll relate these to the moment problem in mathematics. So we're going to go from wave functions to measures and to the moment problem in measures. And then I'll explain how the numerical bootstrap in quantum mechanics, addresses issues of the moment problem. And then I'll show convergence in examples. And then why does it work? It's not clear why does it work. There's no proof yet. But when it works, it seems to work remarkably well. And there will be surprises in the end. We have some new work where we see some surprises, meaning that the bootstrap gives solutions to problems that we didn't expect, and then trying to figure out how that works is actually what we're doing right now. So let's start with basic observations of classical physics, not even quantum mechanics. So if you consider a classical Hamiltonian and you start with an initial condition, you can do averages over a trajectory. So time averages over the long term, the type of stuff that we'll do in statistical mechanics. So if the trajectory is bounded for all time, then the expectation value of any time derivative is 0. So in a Hamiltonian system, the equation of motion of f is the Poisson bracket of f and h, and then the expectation value in the sense of time average of this Poisson bracket will be identically equal to 0. Okay, so the proof of this is simple. It's the theorem of calculus. So the expectation value of f dot is 1 over t prime minus t, integrate over time, and then you get the difference of f at the final time and the initial time divided by the total time. And if the numerator is bounded, the denominator can go to infinity in infinite time, and therefore the expectation value of f dot is identically equal to 0. And then the point is that we only need to know the equations of motion to find a lot of averages of functions without actually having to solve the dynamics. Right, so you don't need to solve the dynamics to make these averages equal to 0 because the expectation value of any time derivative is 0. The same structure is actually true in quantum mechanics. The expectation value of O dot is equal to 0. Now there's two averages here. There's the usual averaging over time, and there's also the average that's intrinsic in the probabilistic nature of quantum mechanics. If you're already in an eigenstate of the energy, the system is stationary, and then you don't need to do any time averaging any longer. Okay, so the problem is that to apply the theorems that one does in classical physics, you need some equivalent notion of a quantum version of boundedness. So wave functions need to be sufficiently localized. The operator needs to be sufficiently bounded on the Hilbert space relative to the energy basis. And then if you think in terms of bound states, you actually need proper bound states whose wave function decays exponentially at infinity, and not bound states at threshold that decay only polynomially at infinity. Okay. So most systems that we care, we're looking for proper bound states, and the bound states at threshold are very special, and then you get the continuum, let's say, of scattering, and then I don't know how to solve the problem of scattering yet. So we're looking into it, but we don't know how to do it. Okay. So to do that, we need a Hamiltonian to evolve the system in time. And the typical problem in quantum mechanics is to determine the spectrum of the standard Hamiltonian. The Hamiltonian, which is the Laplacian plus a potential. Okay. So there's nothing new here. And in this case, the following are true for eigenstates of the Hamiltonian. If psi is an eigenstate, then H acting on psi is the energy. It's true on the left and on the right because H is self-adjoint. And then you basically get equations this way that relate expectation values of H times O and O times H. And the expectation value of O dot, if you use the Heisenberg equations of motion, is the commutator of H with O. And then because of this equation where H, O, and OH all pull out an E, you can check that the commutator expectation value is 0, but that's the expectation value of the time derivative O. So the right-hand side, in the sense of this commutator HO, is an operator that can be computed explicitly, and therefore you get a lot of expressions for averages automatically from knowing that you're in an eigenstate of the Hamiltonian. So a lot of expectation values are 0, meaning a lot of operators have 0 expectation value for a lot of for these eigenfunctions. Okay, let's go back to classical physics. If you actually take the Hamiltonian, and since the Hamiltonian is conserved, and you multiply it by any function, then you just pull the energy and the F. So that's very similar to the one that you would have in quantum physics, where you just can pull the energy out of an expression. So this is true on a trajectory. So we're using a microcanonical ensemble. Okay, so you fix the energy. So the example is the harmonic oscillator. You take all functions being generated by polynomials of powers of p and x. You can compute the time derivative by the equations of motion, and then you get the constraint that p squared plus x squared is twice the energy. And then whenever you see p squared, you can get rid of momentum in favor of x. So you can basically remove the powers of p where n is bigger than 2 and replace them by powers of p where p is power 1 or power 0. Okay, so the statement is that, you know, if you want to understand the functions on this trajectory, you don't need to go to the full f and m. You can basically reduce it to p to the 0 and p to the 1 by using this constraint. So that simplifies the problem a little bit. So for example, you can take x to the m, and then at least in standard systems, f1m is p times x to the m. That's proportional to the derivative with respect to time of x to the m plus 1 with respect to t. So f1m, the expectation value is 0. So in some sense, we only need to determine the powers of x to solve the problem of the functions. And if you take the derivative of this f1m, you get an expression which involves p squared and x to the m plus 1. And then you do this trick of replacing p squared by the energy and x. And then what you see here on the right-hand side is that if the expectation value of f1m dot is 0, then there's a relation which is recursive that determines the moment of x to the m plus 1 in terms of the lower x to the m. So let me show you how this looks. This is the recursion. So if you know x to the m minus 1, you can compute x to the m plus 1. And then the expectation value of x to the 0 is the expectation value of 1, which is 1, the constant function. So you can actually determine all the even powers. And then because you're in the harmonic oscillator, x and minus x symmetry guarantees that the odd powers will be 0. And then you can just solve recursively and get all the even powers of the x to the 2n. And then you get some, you know, recursion in terms of 2n factorial and factorial and factorial. And you can actually check directly that this is the correct measure that one would get from taking the trajectory and computing the dx over p type measure that one would use in quantum mechanics. And this is similar to a semicircle. In the semicircle, you will get something similar, but there's some extra power of n plus 1 in the denominator. And the difference is that in this equation, the square root measure is in the denominator rather than in the numerator. But you know, it's perfectly solvable. So in this case, you know the energy, you know everything. You don't have to do any computation, and you get all the even moments of x automatically by recursion. So this is the spirit. So the same type of recursive structure should be true in quantum mechanics. So you can, in principle, reduce it to powers of x. The other complication in quantum mechanics is that you cannot just pull functions. There's ordering ambiguities. So when you resolve these and are careful about commutators and everything else, it makes the equations longer and the recursion has more terms. And in principle, you can apply these to higher dimensional problems. So what's different is that beforehand, let's say the expectation value of x to the s minus 1p was identically equal to 0. And now you see that it's not identically equal to 0. There's a correction when you use quantum mechanics. And then there's this imaginary value, and this has to do with the ambiguity because x to the s minus 1 times p is not Hermitian, so it can have an imaginary piece. And then it's exactly that type of ambiguity that shows up here. So you have to think about this imaginary part as a quantum correction. And then when you do for more general potentials, usually you would get some recursion that uses p squared, the equations of motion. And then there's this quantum correction that comes from these normal ordering ambiguities, if you want to think about it that way.
Can I ask a question?
Yes.
This will not work on for a particle on a circle.
I'll tell you how to work with a particle in a circle later on.
Okay.
This is the first step. If we're doing just a regular potential, I'll explain the particle in a circle problem later. We're just doing things on the infinite line for the time being. Okay.
Okay.
So if the V is polynomial, then you can get a recursion, and then the recursion will express the higher moments of X in terms of lower moments, and then use this trick of replacing P squared by the expectation value or by the energy and some structure related to the potential. So you do get a recursion, but these quantum corrections are important. Let me tell you what they actually do in practice. These are the things that are actually responsible for tunneling, because what you see here is that this grows with M. So for very large M, this number is getting bigger and it dominates over the potential in some sense. And that's exactly what the tunneling region is all about. That the moments can grow with some big gamma function. It's the part where you tunnel into the region. So these corrections are really important in quantum mechanics. In classical physics, this is what you throw away, these two pieces. Okay, so now let's go to math. This is the moment problem. So if you're given some expectation value of X to the M, the problem is to find a positive measure such that these expectation values are actually the integral of a normalizable measure of X to the N d mu. This is a classical problem solved in various different types of spaces on a line by Stieltjes, Topliss, Hamburger, Hausdorff. So you have to use the infinite line, the circle, the half line, and the interval. So those are the 4 types of different topologies for a one-dimensional problem. And each one of them has their own complications. So they're slightly different depending on the topology. We'll start with the one on the infinite line, okay? And then I'll tell you a little bit about 2 of the other 3. Okay, so if you have a wave function that is normalizable, you can compute directly the measure. You would just say that the measure is the wave function squared. So knowing the measure, so if you know mu, it's the same thing as knowing the wave function in many cases. So barring degeneracies, the wave function can be chosen to be real, let's say, and then you take a square root and you make sure that at the nodes of psi, that there's a proper change of sign of psi, and that and therefore, if you know mu, the square root is usually a well-defined object if you're careful about how to take care of the crossings of 0. So when there's a 0 in mu, how do you deal with that? Okay, so positivity of the measure is roughly equivalent to unitarity, is that the probabilities in quantum mechanics are positive and normalized. So if the measure is positive, that's roughly a statement similar to unitarity. So there's a sufficiency condition, which is that, you know, if you take any square integrable function and you integrate it over the measure d mu, that square function should, you know, be positive when you integrate it. So if you take fx to be all polynomials, this is equivalent to positivity of basically saying f is a polynomial of x, and then you expand this, you get a quadratic form in the coefficients of the polynomial. And then what that means is that you can read a quadratic form. And if you have a quadratic form, you can say that the positivity of the original problem is equivalent to the positivity of this quadratic form. And then for this particular problem of polynomials, you have this so-called Hankel matrix, which is positive, and Hankel matrices are ones that where the anti-diagonals have equal entries. So it's a special type of matrix where the diagonals have equal entries. And then this needs to be a positive matrix. And then there's theorems about existence and uniqueness. This is a necessary condition, but it's also sufficient to find a mu. And what that requires is some bounds on the growth of the moments. Roughly stated, the measure mu needs to roughly decay exponentially at infinity. And if that's kind of satisfied in some sense, then the measure is unique. So this condition is actually not only necessary, but it's actually sufficient. So if you prove positivity of this matrix, you're done. Okay. And then the problem of whether the measure decays sufficiently fast is usually bound state problems in quantum mechanics. They're satisfied. So in principle, if you solve the problem, you have a complete solution of the measure. In practice, it's hard to find it because knowing the moments, going back to the measure requires some complicated inverse Laplace transform and some other stuff like that. It's kind of messy on how to get from one to the other one, but it can be done. Okay. And then positivity of M requires positivity of all principal minors, and this is where you put in numerics, that you start truncating the matrix to minors of ever bigger size. And then what that means is that this is what the numerical bootstrap does, is to basically gets the energy and the lowest moments, let's say, not determined by recursion, and then you check positivity of principal minors up to some size of the matrix numerically. The test fails, you reject the data, and if it succeeds, you keep it and check to higher size matrices. And there's a weak notion of convergence going on here. Let me see. Let me go here first. And that is that for a k by k matrix to be positive, and we can call this the level of the test, the determinants of its principal minors need to all be positive. So the minors are nested inside each other. So if you guess data that survives a level k, then that's necessarily a subset of the data that survives at level k-1. So once you discard something, what's left over, you don't need to recheck, but you keep on kind of shrinking down the space. And then the two sets of equations are kind of the dynamics, the recursion, and then the positivity. So you just need to put these two pieces of data, solve the recursion numerically, check positivity numerically, and then increase the size of the matrices as you reduce the available parameter space. Okay, so how do you check if this works? The first thing I do usually is I go to a model where I know the solution and I check how well the system performs. So we tried that. So we did this with the harmonic oscillator. So the blue one is when you do 2 by 2 matrices. And then here I'm using the tangent of the determinant. These determinants grow very quickly, very fast. So this is basically something that gives you a step function that tells you whether the sign is positive or negative. So if you do with 2 by 2 matrices, the first thing that you get is that the energy is positive. So for E less than 0, you don't get a solution, but we expected that. And then k equal to 4. So when you have the up to the fourth moment, you start finally seeing a little dip. So it tells you that the energy cannot be 0, that there's some quantum corrections that push it up, but you're still below the 1/2. 1/2 is kind of the energy of a typical harmonic oscillator in standard units. And then the idea is that once you start going to higher matrices, you start seeing that there's quantum corrections that push you away from energy strictly equal to 0, and that there's some 0-point energy. And then you move a little bit more to the right. When you increase k, you see that you start getting a bigger chunk of parameter space carved out. And then once you go to k equal to 8, you start, opening windows that are kind of negative and then positive again. And then for k equal to 10, you start opening new windows. So you start seeing that there's some discreteness in the spectrum. Okay, how does it look like? You can zoom into the ground state, and then the convergence is fast. So, I have some number of digits here. If I did this with the 20th moments or 20 by 20 matrices, I can get some pretty good step function over here. I increase the size of the matrix a little bit, and then to the left and to the right, I shrink the space. And then when I go to k equal to 24, I shrink it even further. So, I'm gaining digits pretty quickly. So this is what happens with the approximate spectrum once you try, different levels. This is kind of with 2 by 2 matrices, then like 5 by 5 or 6 by 6, and then you keep on increasing the size of the matrix, and then you see more and more levels popping up exactly at the right values. And then the windows, once they open, they start shrinking, and they shrink fast. And then you see the usual comb of the spectrum, which is equally spaced. So what you see is that you can get not only the ground state, but a lot of excited states. And that convergence seems to be very fast. And then there's numerical issues, which is if you take the typical wave function, it decays like e to the minus x squared, asymptotically far. So the powers of x, their moments, grow like a gamma function. And when n is equal to 10, it's not too bad. When n is equal to 100, it's pretty bad. So numerically, what happens is that this grows very, very quickly, the moments. So the first time we did this run, we didn't realize this. And then we were using, the usual double precision, and we're getting all kinds of stuff that we thought, hey, this is great physics. And then it was just all numerical artifacts, because you need to go to 60, 80 decimal places of precision arithmetic just to make sure that the cancellations that need to happen. So the second statement is that if convergence is fast, you can miss the next step from undersampling. So let's say you are sampling every 0.1, and then 2 points survived, and then you increase the size of the matrix. And then if you keep the same grid size, then you might miss completely the region that survives. So if the region shrinks very quickly, you need to zoom in onto the region that survives and resample very carefully that region. So this is a statement about numerical issues. You can miss the next step from undersampling, so you need to regrade as you proceed. Again, this is not a deep statement, but it's something that one needs to do carefully. The next step we did the hydrogen atom. And again, we kind of did brute force. The hydrogen atom is now not on the real line, but only on the half line. Again, we can check powers of R, but now some can be negative because of this 1/r squared. And then in this case, if you actually look at the recursion relations, it's determined completely by the energy. And then we did the dumb stuff, which was just check the same Hankel matrix and check what we get. And then for L equal 1, you do 10 by 10 matrices, 20 by 20, 30 by 30. You see that the energy levels start shrinking. You start getting more resolution, and then you're seeing the states come up from the calculation, and then we're doing good. And then if you have different angular momenta, you know that the energy levels are degenerate, so you can actually check how quickly they converge for different L to see what's going on. And then we saw that the higher L converge more quickly, and if you look at this more or less, you see that you're converging more or less exponentially to the answer. So this is a log plot on the left, and then the size of the matrix is on the right. And then what that means is that if you go to 40 by 40 matrices, you can get a precision of 10 to the minus 10. So you care about things beyond the 10th digit, you have to go higher. But what you see is that for L equal 1, it kind of goes slow. And then this was puzzling to us. Why would it work this way? There's actually deep math in that statement eventually, but we also made a mistake, and I'll tell you about it later on. So we tried something where we could compare even more things up to L equal to 8. So that's the, n equal to 8 energy eigenfunction, or the n equal to 9 in the principal number of the hydrogen atom. And then obviously if you go to higher angular momentum, it converges a lot faster. And then there's this pattern, which I didn't tell you about, which is that the left and the right don't really converge at the same step. The interval doesn't shrink symmetrically, it kind of shrinks asymmetrically, but both of them converge. There's this curious pattern of left-right shifting that we don't understand, of which one is closer to the right answer at a given time. But eventually one side wins, which is usually from the left rather than the right, so from the low energy. Again, convergence seems to be exponential. And then you can actually compare the different L's. And then here you see that, our error bars for L equal 1 are a lot poorer than the error bars for the other one, which you can't see them any longer. And then to make the energy spectrum more visible, we put a logarithmic scale of minus the energy over here, so that we could separate the levels so they wouldn't crunch up completely, but we can in some sense recover the spectrum of the hydrogen atom. And then the question is, what happened with L equal to 0? And when we just did this brute force like we were doing, we found that there was no constraint no matter how big the matrix worked. And I'll tell you that we did make a mistake. But before that, we also did the double well. The double well is not analytically soluble. You can compute the recursion rather easily, but there's a lot of things we know about the double well from, let's say, tunneling calculations and semi-analytical methods and approximations and asymptotic series, where you can actually get a lot of good knowledge of what's going on. So the goal for us was to discriminate the non-perturbative splitting when you have a double well potential and there's some tunneling. So the question was, does the bootstrap see the tunneling contributions? Can it, tell the difference apart between two nearly degenerate states that are very close to each other? And then eventually, when we went to sufficiently high matrices, we could see the splitting of the two energy levels. And here you have the expectation value of x squared on the vertical axis and the energy on the right. And then this dashed line is if you just do classical solution and do the classical averages, and then just try to understand the expectation value of x squared versus e. And then this is a special case where there's a lot of symmetry. So the even moments have a recursion on their own. So you don't need the odd moments, and the odd moments, because of symmetry, are 0 anyhow in this double well potential. Okay, so we go there. This is at some value of g. This is the energy spectrum versus the coupling constant, and then we make the coupling constant bigger, meaning it's the double well is deeper, and then you see that there's two energy levels kind of converging for each energy level, which is what you would expect. You have two double wells, each one of them is like a harmonic oscillator, and there's some very small amount of tunneling between them. Okay, so you can compute in this approximation of perturbation theory of the single well potential, harmonic oscillator plus corrections, and you find a perturbative piece up to, let's say, second order or third order perturbation theory, depending on how you count it. And then this is in, and let me remind you, this is in this Hamiltonian where the coefficient that we're tuning is the one of x squared. Okay, so G big is more classical. So that's why the perturbative series goes like inverse powers of G. So 1 over G is the one that's behaving more like H bar, or square root of G is the one that's behaving like 1 over square root of G is the one that's behaving like H bar. Okay. Okay, so the point is that there's a perturbative piece, and that means you don't see tunneling, and then you need to include tunneling to see that the degeneracy split between the two, between the even and the odd wave functions. And to second order non-perturbatively, the energy split is this usual exponential. In our units, this has a g to 3/2. There's a correction to the exponential, which is counts as two loops. And then there's this g to the 5/4, which is the usual measured term that shows up when you're doing these determinant calculations non-perturbatively. And then we needed this term, this additional correction, because our values of g are not that big to get a good match to data. So this is the ground state energy versus G. There's the lower ground state and the higher ground state. So you put this data in.
You were showing us the instanton calculation there.
Yes, this is the splitting in energy.
Two loop instanton. Okay.
Yes, so it's an instanton plus the two loop correction on top of it. Basically, we copied it from the book. People did this a long time ago and they got good at it, and they've done,
Yeah, no, I was just checking, sorry.
Yeah. So if you actually plot the energy versus G by using these two splits, and you look at where our data falls, the dots are our data, and then the the two color lines are how the energy matches. And you can also look at the splitting of the ground state energy that we compute numerically from our data. And then you can compute to this two-loop prediction, and then you get that the instanton thing is pretty good. And then we get, a splitting in the energy, which is, 10 to the minus 2 relative to 12. So we're seeing, good precision on the splitting of. Eventually, it gets hard to do calculations for G very, very large numerically. But that's a different issue. Okay, again, we can look at how well it converges, but now you have two parameters because you have the energy and the expectation value of x squared. So now you have to scan both in E and the expectation value of x squared. And you can look at where we're supposed to find, and you find these islands. And then how do you measure convergence? You just measure the area of the allowed region by, computing the principal axis, and then order by order. And then you try to see how big is the area that survives. And then the area that survives, still decays exponentially. So this is how you compute it. So that tells you get very close to the right answer. And then the PC mass here is this notion of the area, which is kind of some central mass of the little blobs that you get with some ellipsoidal approximation. Okay, so, we have a bunch of islands and the convergence is good. And then you increase the size K, and then, the higher islands means higher energy. So higher energy always takes a little bit longer to converge. So they always kind of show up later in the calculation. Okay. Now we go to the question that was asked, which is how do we deal with the periodic potential? So instead of moments, we need to use functions that are better adapted to the periodicity of theta. So we use trigonometric periodic functions. So again, if you have the norm of f of theta squared in mu greater than or equal to 0, you use a Fourier decomposition of f to get that f of theta is some, sum over Fourier coefficients. And then you put it in the measure and you get a quadratic form in terms of the Fourier coefficients. So the condition we need is that this matrix of exponential to the I theta, e to minus I theta, now with the diagonals being constant, as opposed to the anti-diagonals being constant, this is the one that needs to be positive. And because the diagonals are constant, this is called the Triplets Matrix.
Can I ask the question again? Yes. You have converted it into a trigonometric moment problem, from what I see.
Yes.
Okay. What happens to the domain problem? I mean, any density matrix.
I'll show you what happens, because there's something interesting going on. So the point is, we're just doing this brute force. You can ask what you get. And then, for example, one of the corollaries is that any 2x2 minor needs to be positive. So you get, let's say, an upper bound on any one of these moments that says that the Fourier moments are bounded in coefficient by 1. So this, for example, gives you a simple bound to check.
Sorry, I don't understand, because there are, depending on the domain, there are many ground states.
Yes, we'll get to that.
Which one are you choosing when you write?
So that's exactly the question. What does the bootstrap choose? Right? So at this stage, all I'm telling you is how we solve the problem in the sense of what you need to do. And then the domain problem will show up, and I'll tell you what the domain that the bootstrap chooses is. Okay? Which is a different statement than what I would like to choose personally. So what you find is that, let's say you do the Matthew problem, the simplest problem, cosine theta. This is a standard problem in, let's say, tunneling. It shows up in all kinds of places. The pendulum has this kind of potential. The fact that the potential is even means that in principle, you should be able to use the evenness of the potential to make statements about, real wave functions and symmetry of theta to minus theta. And therefore, the sine functions of theta should vanish, and therefore the Tn are real rather than complex. But this is a minor thing. You can also work the commutators, you get a recursion. And then what you see is that, here you have Tn, there's an ntn, here's Tn plus 1. And then there's an n cubed over here. So if you look at that n cubed and you say what happens at large n, what happens at large n is that Tn plus 1 wants to grow because it gets an n cubed relative to Tn. Okay, so the moments really want to get big. So they want to get big unless there's some fine tuning, there's some cancellation. So if you apply the bound that the moments are bounded above by 1, you can basically use that to help focus on the region of parameter space where things are going to go, because what you see is that something is going to go bad if the moments grow quickly. Okay, so this is what you get if you actually just use those bounds for n equal to 2, n equal to 6, n equal to 10. And what you see is that you start getting these kind of regions that are kind of thin regions that survive when you make the Tn less than 1 bounded, and that the size of the regions kind of shrinks as you make the size of the Fourier moment that you're testing bigger. But you seem to have these kind of lines over here. So now back to the problem of what domain you're in. The bootstrap equations don't know that the angle variable is periodic. They just know the recursion. So it works just as well on the covering space. So what happens is that what the bootstrap gives you is the band structure of the potential, rather than, so instead of doing the domain where you would be on a circle, what you're actually doing is the domain where you're in the infinite real line, and you have the different values of the theta angle, and what you get instead is a band structure. So it turns out that the moments are still well defined for any 2 pi region because we use periodic variables, but the domain itself is the full infinite line in principle. So this is what it actually looks like. You get, these regions, and these bands don't go away. They are supposed to be there because in band theory, we know that you're supposed to get some non-trivial dispersion relation. So if you change, let's say, the coupling, and then you use simple harmonic oscillators at the bottom of the potential well, and then you take the maximum and the minimum energy of the stuff that's still in the bound region, and then you use simple harmonic oscillator levels, you see that you get corrections to simple harmonic oscillator, which you expect because cosine is a nonlinear function. And as you increase the strength of the potential, there's still corrections that are perturbative, and then there's also bands, so there's also non-perturbative physics going on there. So the point is that you don't get the domain that I wanted, let's say, which is just a circle. You get the covering space of the circle, and the bootstrap doesn't know what the value of the quasi-periodic variable is. So the problem is, if you went to find the dispersion relation, the bootstrap is, let's say, telling you the polynomials of P, expectation values. But what you would want instead is exponential to the IP. And then Chomakov and Florence studied this problem more carefully, and they found that if you just try to do something brute force, the numerics are very bad. So there's a different way of doing this thing. So what they did is you can assume that the measure has delta function support on various P that are split apart by some value. And then if you have this delta function support, then there's going to be some constraints that you can get on the.
Can I ask a question again? I'm sorry. The wave function on a circle, whichever, choose some domain, but the wave function of the circle is L2. Okay? But if you pull it up to the covering space and just use the measure on the full line, which is the covering space here, one will get infinity. Okay.
Right. So the point is that the measure we're using is always on an average inside the theta from 0 to 2 pi. So even if the wave function is quasi-periodic, you're still doing things on the circle size. So you're doing the integral on the circle size, even though the wave function itself is a wave function about the full covering space. The wave functions are not L2 normalizable in this case, but the moments that we study, because you're restricted from 0 to 2 pi, are.
Okay.
Okay. Again, the point is you get the band theory. You don't get the let's say the L2 spectrum of particles on the circle. As I said, the problem is to find the dispersion relation, and they seem to have a method. And then the method looks for probability distributions in momentum with delta function support rather than continuous distributions. And then that one can match to p moments, and then they are able to get some data on the band structure this way, and they compared it to other numerics, but they don't understand convergence very well yet. So there's an issue of how does one actually do this in practice. Okay. And now I'm going to tell you that when we did the problem on the real line for the hydrogen atom, we missed something. So I'm going to do a toy problem first, which is solve the harmonic oscillator on the half line only. And then what happens is that now, apart from the even powers of x, since you're on the half line, you also get odd powers of x. But the even ones are the same as before if you use the standard recursion. So in principle, we already know the energy levels from the even, but what happens with the odd moments? And then this is where you can just add them to the recursion, and then you start, use the same matrix that we had before. You take the first two odd moments, A1, A3, and then you take your favorite energy, the first excited level, and then you start dicing and slicing some regions, and then you get these things that all seem to cross the origin and go through here. It's the same Hankel matrix as before, but now something interesting is going on, is that even though we're supposed to converge here, we're missing something, because we seem to actually be getting all this region from this point all the way to 0.
So what boundary condition have you chosen at the origin?
We haven't. We just chose the condition that says we know the wave functions, we know the energies from the even moments already. And then we're just using that. And then we're just trying to understand how to compute the odd moments having the even moments. Again, this is a statement, but then there's a problem of convexity. If M1 and M2 are positive matrices, so you have two solutions to the recursion, then if you take alpha M1 plus 1 minus alpha M2, that's also positive. So if you have two positive matrices, this is also positive. And we know that if you put at the odd moments at 0, that's a solution to the bootstrap equations that we had, because that was the one of the full harmonic oscillator. So it turns out that whatever you do, you get a matrix where everything with odd powers being 0 is also a solution to the formal problem that we have. And turns out any linear combination solves the recursion relations. So the upshot is that if you're doing this, you're solving an incomplete problem. So what's going on is that you get a complete line from whatever solution it is all the way to the origin. So the problem is that the function x is positive on the half line. So if you're careful, x times the Hankel matrix we had before, or this also needs to be positive. So if we had read the Stieltjes problem more carefully, it tells you that the conditions for the measure to be correct is that you have to check for positivity of two matrices rather than just one. There's the positivity of the matrix we had before, and one where you multiply by x, because x is also a positive function on the real axis. Okay. So if you ask what happens when you add x here, it turns that the diagonal components become the odd moments, and the odd diagonal components can become the even moments. So beforehand, positivity was giving you relations that bounded how the odd moments would behave in terms of the even ones. It gave you upper bounds of the odd moments. On the other hand, if the odd moments are on the diagonal, what you get is lower bounds on the odd moments, because the even ones need to make the matrix positive. So if the odd moments are too small, these determinants are going to be negative. So what happens is that when you add this matrix, you start carving out space from the top rather than from the bottom. And then you carve out the two pieces. You actually put the correct values from just computing the integrals, let's say in Mathematica. And then you see that with, the first even moment and the first few odd moments, you've carved out a really small slice of parameter space that survives. And then you've determined the odd moments. So it turns out that for the odd moments, you need to have two positive matrices rather than one. There was the original positive matrix plus one more. And then you can say, oh, what happened to the harmonic oscillator? We had this problem with L equal to 0. And then use the second Hankel matrix. And then suddenly you start getting all the energy levels. So we need to redo our convergence analysis.
But I expect a one-parameter family of solutions here.
No, not anymore.
Because of the boundary conditions, I can choose. I don't need to choose Dirichlet. I can use an arbitrary parameter on the boundary.
Right. So this is what we're studying right now. If you actually do the hydrogen atom carefully, like we did, then so long as the angular momentum is bigger than 1/2, I think that's the correct value, the Hamiltonian is essentially self-adjoint. And that means that you don't get to choose the boundary conditions. There's only one set of boundary conditions, which makes the Hamiltonian essentially self-adjoint. So it turns out that for L bigger than 1/2 or L bigger than 1, the Hamiltonian is essentially self-adjoint, and therefore there's only going to be one solution. Then you can ask, what does this system do at L equal to 0? So if you analytically continue in L, you can do between L0 and L equal to 1/2 and try to understand what happens there. It turns out that the bootstrap spits extra solutions that are not solutions to the naive boundary conditions that one would have. And this is where one ends up talking a little bit about the mathematical properties of Whittaker functions. And what happens is that one boundary condition is better behaved in that the wave function vanishes near the origin, and the other one has a polynomial singularity near the origin, but the singularity is square integrable. So you actually can find measures, but if you look, for example, like the expectation value of 1/x, the expectation value of 1/x becomes divergent in these measures, in these other measures, and therefore you need to modify things a little bit to make it work. But the point is that if you just do things with force and you don't, and if you ask what's the bootstrap doing, it can find these other boundary solutions of these other type of stuff. Actually, when we're trying to understand this a little bit better, we found out that for the recursion to work as given with the usual commutators, you can ask, let's do the commutators correctly, not just with formal symbols X and P and do the commutators, but use integration by parts to see what's required to make the recursions work exactly as we describe them. And what that requires is that it self-selects the Dirichlet boundary condition. That's the one that the moments actually, the naive moments that we have solve. If you choose different boundary conditions, you need more initial conditions, and you need to loosen up some of the recursion in some places because some of the recursion equations are going to be modified by the boundary condition in a non-trivial way. But we haven't understood the complete story there. We know that the system self-selects, let's say, Dirichlet boundary conditions. We did this for the area function, and it worked just great. And then we were trying to find, let's say, the Neumann boundary conditions or the Robin boundary conditions, and we found a numerical mess that didn't give us what we wanted. That doesn't mean that it's not doable. That means we don't understand how to do this correctly yet for these more general boundary conditions. So part of the story is that the bootstrap, in some sense, requires that information in there. And the point is that the bootstrap is not this machine that's kind of impervious to details of boundary conditions and more careful analysis in quantum mechanics. You actually need to put that in to make it work and to understand what's going on. It's the same way that we got actually quasi-periodic functions, is that the bootstrap doesn't know the periodicity of the domain, so it picks the domain that's compatible with the recursions, the maximal domain that's compatible with the recursions. And then you have to work very hard to kind of split it apart into the proper pieces to make it work. Okay, other remarks. The bootstrap also has seen problems in matrix models. So if you do large N and you use factorization, you also get recursion, and there's also some positivity constraint that you can use. One of the big differences between this quantum setup and this other setup is that in these large N matrix models, you end up using loop equations, which are nonlinear. So the problem of the recursion is nonlinear, and that's less useful for numerical methods. And then they were able to show that you can turn the problem into a more complicated problem of nonlinear semi-definite programming with some extra bells and whistles and extra information, and then eventually they can find solutions. And it converges to solutions of the matrix models that have a positive measure on the real axis and don't have complex cuts or anything like that, but they have only cuts on the real axis, and they have a positive density of eigenvalues. Okay, That's it. What's the conclusion? You know, I told you a little bit about the quantum, how the bootstrap works in quantum mechanics, and I told you that it deals with some of the issues in math that will be associated to different problems in its own way, and then we're still trying to understand some of these things. The method works by a mix of recursion plus unitarity, positivity if you want to think about it. And then it works very efficiently, it converges fast. And I think it converges very fast exactly because the moments grow so quickly that the tunneling region kind of plays a plumbing role in how these things evolve. And the big issue is let's say you have to search in a 10-dimensional space of initial guesses. You need to find ways to find efficiently where to start. And then, as I said, we're also exploring further the problem on the real axis because this is already very interesting and has some problems. And then we're trying to find, let's say, 2D problems with a small search space that are not just two copies of a 1D problem. That also works, but and the fact that the boundary conditions are kind of self-selected in some sense by the bootstrap problem means that if you want to understand boundary conditions carefully, you have to work really, really hard to figure out what's going on. So in some of these questions, that's what happens. So this is where we're at. Pretty soon we'll have new stuff on, you know, the real axis and this issue with understanding better when does the recursion work like it's supposed to and when does it not do it. Okay, I think that's it.
Okay,
yeah, that's it.
Okay, thank you very much.
Wow, I finished on time. That's amazing.
Perfect timing. Okay, are there any questions?
Can I ask a question? Because it's a very interesting talk. I want to understand. So why can't the domain of the Hamiltonian, that is boundary condition, be incorporated in the choice of the density matrix? The quadratic form you are defining, which is positive, depends on the density matrix. One can incorporate the domain problem right there. Okay? The density matrix can take care of the domain.
Right. So the question then is, how do the recursions change when you change the boundary conditions? And this is where, if one is more careful about how one computes the recursion of the moments, and not just use symbols to compute commutators, but actually do the calculations and integrate it by parts and check for let's say, self-adjointness and stuff like that, you see that some moments will get contributions from the boundary value of the wave function.
The Hamiltonian, the domain you have chosen for the density matrix is in the domain of the Hamiltonian. There will be
right. So let me go back to the problem. Let's say I'm trying to solve this. Where's my? Okay. So let's say that I'm trying to solve this problem with this second derivative of x, and I want the second derivative to be self-adjoint. Then that usually puts the Robin boundary conditions on the wave functions that are solutions of H. So the Robin boundary conditions relate the function at the boundary with the first derivative at the boundary, and there's some coefficient that relates it. But formally, if you just use commutators of derivatives, you don't see that until you actually put it in integrals and you actually compute things and check for self-adjointness. So for example, the only case where the momentum operator, IDX, is how you call it, self-adjoint, is with Dirichlet boundary conditions.
It effectively puts in a delta function potential.
Well, that's exactly the point. You have this kind of delta function potential. So, but the point is that you don't have delta functions in the recursions.
Yeah, I mean,
so,
that is really,
well,
yeah.
you could have. I mean, they are
included
in the integral.
That's the
as
very
I said, this is one of the
activity,
things that we don't know how to do. We know how to do polynomials and use the measure problem on Stieltjes with regular polynomials and not, let's say, with absolute values. Again, the problem is, how does one actually put these precisely in the recursion? So the recursion needs to have that information somewhere, because in the end, we're going to be blind to that and just check for numerical values in terms of this positive matrix that's computed recursively somehow. So all of that information needs to be encoded in the recursive solution of the X, and that's the part that we haven't solved yet.
Is it the problem that ddx, the domain of the Laplacian, is not necessarily the domain of the momentum?
Right.
It can differ. That is a problem, if I understand. Yeah. Okay. Now, one more question. You were talking about convex sets at some point. Okay?
Yes.
Where you were taking. So why don't it suggest that it's better somehow to work with, say, Weil algebra, boundary operators, and then you have all these Krein-Milman theorems, extremal points of convex sets, and so on. There's a whole
there's a little bit of a caveat there, is that we don't necessarily have the recursion relations there. The recursion relations are nice for these non-compact objects rather than for other things. So the question is, on an example by example basis, one uses sets of functions which can be computed recursively from each other. That's really what it boils down to. So when we could use recursions on the trigonometric ones, the potential had to be nice in trigonometric functions, right? So for example, some other people have tried to use these for Hamiltonians, which are not, let's say, polynomial in the X, but which have exponentials of the X, which show up in, let's say, mirror symmetry. And there, what happens is that the wave functions, whereas they do decay exponentially, you don't do moments of, let's say, X, but you do moments with exponentials of X. So only a finite number of constraints show up, and then the method doesn't converge in that case. So these are these things that show up, let's say, in matrix models from Seiberg-Witten curves that you also need to quantize a Hamiltonian. And then in that case, you can get a lot of constraints, but you don't get convergence to the exact answer because some things become non-normalizable, and therefore you lose the power of the positivity of the constraints.
Another remark which may be not relevant, but let me say, the whole thing looks very much like a treatment of large and matrix models, okay, is or related to large and matrix models, but there is a choice of the Hamiltonian which is going into the problem, okay. But for large and matrix models, there is at least a claimed solution for the large and limits, okay, by Gross and Rajesh Gopakumar, okay, which gives you the solution in terms of Kunz algebras. Okay? Yes. I don't know whether it has any relevance. I'm just asking.
Yeah. Okay. So when you use factorization and that additional information, the group of people, let's say Javicki and company, they try to do these for matrix models and with the usual collective coordinate method, and then they find recursion, and then they also need positivity of some effective kinetic term. And then what they can do that way is find the ground state, because it's only the ground state that satisfies factorization. Once you start going to the excited states, it doesn't quite satisfy factorization. So people are able to study ground states of large N models that way, or large N matrix quantum mechanics that way, and it's some complicated problem, but they can do that.
Okay.
Thank you. Any other questions? I have a small question. You mentioned two-dimensional systems at the end. Could you say a little bit about how this, what changes in the method?
Okay. So, okay, this is a question where I say p squared plus x squared equal to 2e. Now there's going to be two momenta and two positions.
Yes.
So I can only eliminate one momenta rather than two.
Yes.
So now you have to keep three variables rather than one. Okay. And then you have to figure out positivity in something with three variables. So it takes a lot longer to find recursion. The other thing that's not clear is that there's going to be a finite number of initialization data. The initialization data might become infinite dimensional. That might happen, for example, in chaotic systems. If the system is integrable and not quite separable in the usual sense, then there might be some way to say that it's still recursive, but you need to fix both integrals of motion, the energy let's say, the charge.
Mhm.
And then it's still interesting to understand how that would work. So there are systems that are like that, let's say TODA or your favorite integrable hierarchy. And then the question is, if the system is not quite, separable nicely, then that's the type of stuff that could be interesting, even if it's, let's say, classically soluble.
Yeah.
Right. But if the system is chaotic, I don't even know yet if it's recursive. But these convexity constraints will become important because only the extremal points would correspond to, let's say, pure states. And then anything between that's allowed by kind of density matrices would be kind of the type of stuff that shows up from mixed states between pure states. That, so I expect that the interesting stuff will be on the extrema of the convex set that's allowed for each energy, right? That's the point. The convex part is a fixed energy. So you need to search in energy, and then you get a convex set, and then finding that convex set, well, because it's convex, it makes it a little bit easier to search. If it were non-convex, it would be really, really hard. If it's convex, it's a little bit less bad.
Yeah, thanks. That sounds interesting.
Okay.
Any further questions? Okay, if not, then let's thank David again for a very nice talk. Thank you very much.
Okay. See you.
It was very nice to
Bye.
have you.